All right, we're going to get going here on 3.3. Hopefully it doesn't get you too angry with me as you see that all the stuff we've been doing so far, we're actually going to figure out some faster, less cumbersome ways to do this. And so it doesn't mean you don't need to know what we've already been doing with doing the derivatives out using the limit, but we're going to start finding some shortcuts here. After all, I mean, that's a lot of math, is finding shortcuts. Multiplication is just a shortcut to do repeated addition. So that's all we're always looking for, are kind of these shortcuts. So let's take a look here. First off, let's look at what happens if our function that we're looking at is a constant function and we want to find its derivative function. Okay, so what we'd have is limit as h goes to 0 of f of x plus h minus f of x all over h. And then that's going to be, we have to look at this and say, all right, well, this is the limit as h goes to 0. Now, f of x plus h, well, if our function equals a constant, then there's no x, so we can't have an x plus h. That means it's just going to be c. And then f of x is also just equal to c, and this is over h. And c minus c is 0, so this whole thing just equals 0. Okay, so whatever number you put in there for c, so like if it had been f of x equals 7, then it would have been 7 minus 7 over h with the limit as h goes to 0, and that still would have been 0. Okay, and so we find out that the derivative of a constant function is 0. And this should make sense because if you look at the graph over here, a constant function is just a horizontal line, and horizontal lines have a slope of 0. Okay, so let's take a look here. What we're going to come up with now is the power rule. If we have a function such as like f of x equals x to some power, some exponent, then we can simply follow this rule where the derivative of that x to some number n is just that n number out in front times x, and then we're going to subtract 1 from the exponent. So basically what we're going to do is we're going to bring that in out front and then subtract 1 from it. Okay, and so let's look at some examples of this and see how we do this. So these derivatives we've already found, so you can go back and check them, but we did them kind of the long way. So here, 1 over x, I can actually rewrite that as x to the negative 1 power. And so then I can follow this rule. I can bring the negative 1 out front. I can make it x, and then I can do negative 1, and then I can just subtract 1 more from it like that. And then that's going to be my derivative. So negative 1 times x is just negative x. Negative 1 minus 1 is negative 2. So it's negative x to the negative 2, or you can write this as negative 1 over x squared. Okay? So let's take a look at the next one. Remember that square root functions are actually just to 1/2 power exponents. So that's x to the 1/2. And so I can bring out the 1/2 out in front to take the derivative of it, do x, and then I'll have 1/2 minus 1. And this gives me 1/2 x. 1/2 minus 1 is negative 1/2. And so to the negative 1/2 power, the 1/2 power gets a square root. The negative says take the reciprocal, so this is 1 over 2 times the square root of x. Okay? So not so bad there. Here's some more examples. And so we could try these, and I'll do these ones for you on the next page. I'll leave some more for you to try, but I'll put the answers in the notes. So this is going to be bring the 3 out front, make the x there, do 3 minus 1, and that's a 2, and that one's done. So this makes doing these much simpler and a lot faster. Bring the 2/3 out in front, times x, and then 2/3 minus 1 is our new exponent. So 2/3 minus 1 is just going to be then 2/3 times x to the negative 1/3. Okay, so there's your answer there, real simple. Here is x to the square root of 2. So again, don't let that bother you. Square root of 2, x to the square root of 2 minus 1, like that. And so this becomes square root of 2 times x to the square root of 2 times x to the negative 1. We can write it that way, which is just going to equal square root of 2 times x to the square root of 2 over x to the 1. And so we can just basically leave it like that. This would be square root of 2 x to the square root of 2 over x. Okay, and so that'll work. If you had tried to actually do square root of 2 minus 1, you're going to get kind of a, you're going to get an ugly number, so we'd probably just leave it like that. All right, so the next page here are some ones for you to try. Again, I'll go through and solve them in the notes so you can just take a look at them there when you're done. Okay, so here we've got the constant rule. This is a derivative a derivative of a function that has a constant multiplying into it. So basically all you do is just ignore the constant. You just bring it out in front. So it would be kind of like if you had the derivative d dx of c times u, where c is a constant, you can make it c times the derivative of your function. So whatever your function, no, not x there, whatever your function needs to be. Probably should just, actually it might make more sense if I wrote it like this, f of x, like that. And then it's the derivative of your function, and then just multiply it by that constant. So let's take a look at this example here. We have 3 times x squared, and so we want to find this derivative, so we're going to do the derivative d dx of f of x, which is the derivative of 3 times x squared, which we can just bring that 3 out in front, d dx x squared, like that, and then just use our power rule. So this becomes 3 times, bring the 2 out in front, x, and then it's to the 2 minus 1 power, so it's just a 1, and this is just ultimately a 6x, okay? And so there's our derivative function. So we know that f prime of x equals 6x. That function tells us the slope of the tangent line at any point on the graph 3x squared that we want. And in this case, we want what the slope is at 1. So we've got f prime of 1 equals 6 times 1, which is just 6. Okay? So the slope of the line tangent at x equals 1 is 6. Okay? And if we wanted to actually find the equation for that line that is tangent at that point, we just do y equals mx plus b. We know that the slope, this is m, so this is y equals 6x plus b, and what we need to do is figure out what value of b is going to make it hit that line, because we can have any number of lines that have a slope of 6, right? But they aren't hitting that point right there. Any one of those, same slope, but not hitting that point. So we need to find that specific one that is right there, that is hitting through that point right there. So what we do is we use that point. That point happens to be the point when we plug it in. We got to figure out what the y value is. Actually, I think I was doing the wrong one right there. It's this one right here. Sorry. That one has the slope of 6. So we know that's at x equals 1, so we need to find y. So f of 1 equals y, because that's the point we're looking at, which is just 3 times 1 squared. That comes from what f of x equals, which is just 3. So y equals 3. So we need this to be at the point 1, 3, which means we can plug in 3 for y, 1 for x, and solve for b. And so this is going to be -3. Okay, so b equals -3. That means that overall, if we were finding this, it would be 6x minus 3. And that would be the equation of that line right here, this one over here, that's going through that point and is tangent to the curve at that point. So let's look at some more rules. The derivative sum rule. If u and v are differentiable functions of x, so we're going to start Just because it makes it a little easier, we'll start representing functions with just u and v. But basically, this could be like f of x, and this could be like g of x, okay? They're just functions. And then their sum, u of v, is differentiable at every point where u and v are both differential, and at such points, you're basically just going to take the sum of the individual derivatives. So it's almost like you can distribute this through the parentheses. You can multiply through. Like I told you, this d dx here thing, it's an algebraic structure basically. You can multiply it, not multiply it, but operate it onto u and operate it onto v, and like distribute it through the parentheses and just get this over here. So let's try this. Let y equal uv, where u of x equals x to the fourth and v of x equals 12x. That means that y equals x to the fourth plus 12x. And then we can find dy dx by just doing d dx of x to the fourth plus the derivative of 12x, like that. And so x to the fourth becomes, bring the 4 out in front, x, and then subtract 1 from the exponent. And then the same thing here, where this time it's a 1 in the exponent, so we bring the 1 out, right? We take it inside the 12, so really what we're doing here is of x, and we're bringing the 12 out in front. So it's going to be 12 times, and this exponent up here is a 1. So we're bringing the 1 out front. 12 times 1 is 1, and then 1 minus 1 is 0. So this is x to the 0, which is just 1. Anything to the 0 power is 1. So 4x to the third plus 12 then would be the derivative of that. You just do each derivative individually, okay? And so this is very useful when you're dealing with polynomials. So like if we were going to do the derivative of this polynomial, it would just be the derivative of each individual term and then the sum of those individual derivatives. So doing it quickly, y prime, the derivative of this would be x to the third becomes 3x squared. 4 thirds times x squared, you bring the 2 out, that's 8 thirds, x to the first. This is negative 5 times x, and again, the derivative of just x is going to end up just being 1, just like it was up here. You'll get an x to the 0, bring the 1 out front, so this is just a minus 5. And then the derivative of a constant is 0, so that's 0, okay? And that's basically what we have here. And remember, this y prime, oops, that wasn't a good prime, y prime is the same thing as f prime of x, is the same thing as dy dx, is the same thing as d dx of f of x, and so on and so forth, or d dx of y, like any one of these, they're all basically equivalent as far as we're concerned. So what about horizontal tangents here? Does the curve y equal x to the fourth have any horizontal tangents? And so let's see if we can figure out why. Where? If it's going to have a horizontal tangent, that means we need to find when f prime of x equals 0. Okay? And actually, finding these horizontal tangents is actually a very important skill, so we want to get pretty good at this. So first thing we need to do is take the derivative, f prime of x equals, and now x to the fourth becomes 4x to the third. Bring the 4 out front, subtract 1 from the exponent. This becomes negative 2. Remember, we just multiplied by 2, but we're going to actually then just take the derivative of the x squared. So it's 2 times the derivative of x squared. So this is going to be 4x to the 2 minus 1, which is to the 1. And then the derivative of the 2 is just 0 because it's a constant. So that's what we have. So now we set this equal to 0. When does this derivative equal 0? We can factor out a 4x, x squared minus 1, like that. And then we can divide everything by 4, so we can cancel out that 4. And 0 divided by 4 is just 0 still. And so this is 0, this is x. X squared minus 1 is the difference of two squares. So this is x minus 1 times x plus 1, just like that. And there are 3 answers. X can be equal to 0 from there. X can be equal to 1 from there, and x can be equal to -1 from there. Those are all zeros of that derivative function, and therefore those are all places where the slope of the tangent line will be horizontal, it will be 0. So if you look here at the figure, you can see -1, 0, and 1, right? -1, 0, and 1. All three of those places are places where we have a horizontal slope. What I'd also like you to take note of is that each one of these, notice where it's occurring. It's occurring, one, where the graph was going down, but then started going up, or was going up and started going down, was going down and started going up after like that. So that actually will occur a lot, that it'll occur at maximum and minimum points, local maximums and minimums, like the tops of hills or the bottoms of the little the holes or the dips or the craters or whatever. All right. So keep that in mind as we move forward. That is actually something that we're going to start taking advantage of. So next, derivative of exponential functions. So we're looking at the derivative of a to the x. This becomes the limit as h goes to 0 of a to the x plus h minus a to the x all over h. And then as you go through this, you can see step by step, a to the x plus h is a to the x times a to the h, and you can just factor an a to the x out in front, and then the a to the x goes out in front, and then this little part right here, well, this is just a to the x times, essentially what this is the derivative f prime of 0. That's essentially what that part is. Okay, that's that same part right there. Okay, and that gives you basically, ultimately what we have here is the derivative of a to the x is a to the x times something. We don't know exactly what that is just yet, but we'll get there, okay? So the derivative of a to the x is a to the x, and this occurs at f prime of 0. So anyway, so take a look here. There are some little versions we're doing here, excuse me, with different bases, different bases of our exponential function. When a equals 2.5, this will become 0.92, the limit. When a equals 3, we get 1.0. Thus, L equals 1 at some number a between 2.5 and 3, okay? And it turns out that the number where this is going to work out to be exactly that is when that number, that base, is e, the exponential, the Euler's number. This is the base of the natural logarithm, that number, 2.718 something, 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 something. Okay, so it's going to occur somewhere between the two of them. Actually, I wrote this as 1. It should be 1.1. Okay, it's going to occur somewhere between them. So here is 3, here is 0.92, and here, right there, that's where we're getting it to go to 1 right there. Okay, and so what this tells us is that the derivative of the exponential function with base e is just the exponential function with a base of e. So the derivative of e to the x is e to the x. It's the easiest derivative to do, essentially. It just is what it is. Make sure you remember this. Make sure you're used to it, because that's the one that works out. So that is where it ends up being. And so, for example, if you had something like the derivative of 8 e to the x, this becomes 8 times the derivative of e to the x, and the derivative of e to the x is just e to the x. So this is just 8 e to the x. Basically, the exponential function is the function where it is its own derivative function. So anywhere you go, the value you get is also the slope of the tangent line there. So whatever value you get at e to the x at any point, also going to tell you what the slope is. All right, I think I'm going to stop there for this video, and then in the next video, we'll continue on after that. All right, thank you.